the table that I showed to your classmate, some of you, this morning. This is coming from one of the GAs. And he's giving me some information about the submissions of assignment 4. Now, assignment 4 was the assembly problem, you know, with the pins sticking in there and things like that. Or, you know, something strengthened instead of inside of something else. 18% of the people in that class, which incidentally there's 7 of them, that's a smaller section, for an assembly problem, they gave us the product, they gave him the product, and they gave him the analysis, and no part files. And what that means is that he cannot open your analysis file. He cannot open your product file. It's okay for the homework. It's okay for the homework because he's going to make the assumption that you know, your PDF will collect the marks, okay, or at least the relevant marks. He's not going to give you mark for submitting the product file. That's not good. And I say no good because we have said this thing many, many, many times, and I'm saying it again. If you do that on the test, there is no recourse. When you do an assembly problem, you have to give us the product, all the parts that product uses, and the analysis file. If you don't give us any one of those, you have a problem and there's no recourse. That's not good. 18% no good. Because we have discussed this thing many, many times. And hopefully those people who are not here, they will watch the video. Now, 3% of the people were supposed to submit problem 1 and they submitted problem 2. There's no excuse here. 3%, okay, well, that's only 1%. That's okay. I mean, obviously, some people don't read. 33% of the people, that's 13 of them, they do not have the proper naming convention. Our naming conventions is clear. Your student ID number, your last name, and any identifier that tells you what that file is for. For example, if you want to call it PIN, I have no problem. But make sure you have your student ID number and your last name attached to it. Because if you submit something called PIN, your friend submits something called PIN, there's no way to distinguish between them. Okay, we have talked about these so many times. I mean, 10% of the people, no submission. There's nothing I can do about that. The solutions are posted. Okay. The PDF uses a screenshot. Okay. And I think one person submitted zip file. Please don't submit zip files. We're not going to mark it. Okay. We're not going to mark zip files. That's why we named them like that. These are small files. We are not asking you to give us the results file or the results file, which could be gigantic. So there's no reason to zip it up. Okay. Are there any questions? Okay. No questions. Good. Thank you. So today, I'm going to do the last presentation for you on hybrids. Now, of course, if you are you're in this section, obviously some of you, I mean, those people who are in lab section 54 that I met this morning, they have until tomorrow at 11:30 to submit their homework. And those of you whom I met yesterday, obviously the deadline is, what is that, 7 o'clock tonight? Yeah, something like that. Okay, that's going to be the last presentation on hybrid. The question came up on why do we use hybrid? I mean, it looks like these examples you're doing. There is a cylinder sitting on a plate, and a plate is attached to I don't know, to some beam, etc. Well, first of all, these are not far-fetched. If you look at your Mini Baja or your Formula 1 for example, the frame is made of beams, basically. These are attached to gadgets, like the car seat, for example, who, aside from the cushion and things like that, can be viewed as either a bulky object, solid object, such as that cylinder type thingy, or shells. The frame of these car seats, they look pretty much shelly look like. And then this whole thing is attached to the engine somewhere. The engine is neither a shell nor a beam. So maybe you want to model that thing as a solid element. So you're not far-fetched. But let's go further. Let's take a pressure vessel with a big pressure. We have solved this problem. And of course, we use symmetry to reduce half of it, and then took a sector and a 4590, whatever it is. But can you criticize, see if somebody can tell me, why is this not a good design for a pressure vessel? Now remember, pressure vessels, of course, have valves, have openings and things like that. But let's take an ideal situation where, you have a pressure vessel which is of this type. Can somebody shed some idea?
Because stress concentration?
I'm sorry, can you say that again?
Stress concentration.
Yes, where? Where?
At the edge.
That's correct. That's correct. Right here, this is a sudden change in the geometry. Sudden change in geometry causes stress concentration. For example, these may be welded, etc. Still a stress concentration. As a matter of fact, if you remember, this end really bulged up. That guy didn't change that much as far as dimension, but the end bulged up. If the end bulge up, it causes great deal of stress here. The stress concentration magnifies that, and things go nuts. You never see a pressure vessel like this. You see it like that. You see it like this, with curvature, necking, bottles, necks up. This is going 360 degrees. You see it like this. Now, we modeled this thing with shell elements, right? You remember that? We modeled this thing. So if this problem is given to you, you must use shell element to solve it. It's a must. The problem is that shell elements have some assumptions in them. For example, there is no stress through the thickness, or a very small, zero stress through the thickness. The problem is that when you get to these edges, the situation is so complicated that business of zero stress through the thickness is nonsense. So what I really want to do, if I want stresses in this area, for some reason, these shells are totally useless. Okay? You stay away from it, no problem. But close to these edges, we have a problem. Even here, there is a stress concentration. Even here, there is a stress concentration. I drew it on purpose as solid object, but if you have to solve this problem, you solve it with shell elements. However, here we have also stress concentration, and if you want to know detailed stress distribution in this area, shell is going to suffer from the same thing that it did here, except that it's not as bad. I mean, it's bad, but it's not as bad as this. So what do people do? Well, they go do something like that. In other words, the wall of the pressure vessel on the top and over here, where things are kind of, okay, it's not that bad, with shell elements. And over here, where the stress concentration is, where the stresses change rapidly, you use solid elements. Solid element. And what do we call this? A hybrid model. We call this a hybrid model. I don't have a beam here, but that's okay. That's still a hybrid. When you have two types of element present, two types, it's a hybrid problem. Obviously, if you see a beam sitting there, you should model it as a beam, but there is no beam here. Okay. Incidentally, even here, if there are reinforcement, if there are reinforcement here around this thing with some kind of a, you know, something reinforcing it, then you model those as beam, but I don't have it here. I don't have it. Now, I'm going to solve this problem for you. We know how to handle hybrids. We know that. And I want to show you some result. And then I want to tell you that, yeah, this is going to work. We know how to do hybrid problems. We know that. This is end of the week. We have done many problems like that. But these elements that are the default in CATIA, remember CATIA, as soon as it sees something, it jumps on it and measures it, 3D. These are not very good. This, where is it? Oh, here. This is a much better element. Instead of those pyramids, stuff like that. These are called these are not tetrahedral. These are called tetrahedral. Pyramids are called tetrahedral. These are hexahedral. Okay. Now you can do it in CATIA, but not just by saying, "Hey, you do it for me." That's where the advanced meshing tool comes into the picture. If you want to do stuff like that, if you want to do stuff like this, even for shells, and you don't want them triangle like that, and these are poor in general, you have to do advanced meshing tools. Okay? Now, I'm not going to do this thing for you, but I'm going to do that problem for you. Any questions here? That's why we need hybrids, among other reasons. That's why we need hybrids. If you look at the bridge structure, which has got you've got braces and you've got flooring and you've got I don't know, girder boxes and things like that, you have all kinds of elements in it: solid, beams, shells. Okay, what are we going to do this problem? If there are no questions about this, I'm going to do that problem for you. And in fact, you're going to learn a few things that you may never have seen it. Okay? Okay. There we are. We start with a product file. I don't expect you ever to go to the advanced meshing tool. That's why I'm not going to do that second one for you, but that's where it's done. So save it right away. File, say management, save as, desktop, new folder. Okay. What do we call this thing? Lecture section 2. Ooh, section 2. Pressure vessel. Okay, how about that? Pressure vessel. Okay, good. Okay. Oh, wait a minute. Let me ask you a question. This is a hybrid problem. We know that, and that's what we want to do. What options do we have for doing hybrid problems? Can you remind me, please? What options do we have?
Doing it in a part or doing the sampling?
Absolutely, absolutely. Let me do it as a part, okay? I can do it in assembly too, but I'll do it as a part because you get to see the thing that I want to do much better. Cancel that. Cancel that. Let me delete this. So let me start with a part. Okay. And now I'm going to save it there. File, save management. I think I already made the folder for you. Save as. Okay, we may have called it pressure. I didn't call it assembly. That's good. That's good. Fine. All right. You're going to see something that, in all likelihood, you have never seen before. In making this part, you're going to like it. So on that vertical plane, I will sketch. Now, if you look at this drawing, I have 30 inches here, radius 3 inches there, and this is 10 inches. And remember, this is going to be a shell. I'm going to draw that thing and then revolve it. It's called revolve it, right? So I'm going to draw something like that. Where is that guy? Here, and we're going to dimension it in just a second. It was a long day. Started at 8:30. Don't worry, we're going to clean it up. Okay, so let's, first of all, let me make this radius bigger. 3 inches there. Oh my God, this is 0.1. 3 inches. If that looks ugly, I'm going to clean it up again. Okay, that's good. So this height is 30. 30. Okay. And this length is, I think we said 10. 10? Or something like this. It's just that I want to move this thing to there. So that point, control that line, you make it coincident, so shift it to the left, there. Okay, good. So what you see here is this. All right. Now, I want to use shell elements, I told you. So first of all, exit this. We have to be in generative shape design, right? Not in part design. So we go to generative shape design. Okay. And I know how to make this thing, you know, go around. And there it is. See, revolve. Now, I want to do this thing separately. Okay, I want to do this thing, for example, this vertical line to go around, and then this guy to go around, and then this guy to go around. But the problem is that when you select the sketch, you don't have much choice. Look, about the, say, I don't know, z-axis, the whole thing will go around. I don't want that. I don't want that. Cancel. Now, of course, you could have done it. You could have done it as a vertical line, not a sketch. A circle, not a sketch, a circle. You know how to do circles. And this one, and then done each one of these with that. But I want to show you something else because I did actually make a sketch. So let me go back to the sketch. Let me go back to the sketch. Down here, something that you probably never used. I guess not. I don't know. Over here, it says output profile, output feature. You see that? It says output feature. Output feature. You click on it, and you select this line. What it does, when you select this line, it becomes heavier in solid, more heavier line. Look, if I select this thing, it became heavier, different, you know, it's white. And I'm going to do it again. This curve, it became heavier. And this guy, it became heavier. Good, good. It looks like nothing happened except that these lines, when we use this, these lines actually became heavier. Okay, you're right, you're right. Exit. Now let's try to revolve that. Revolve. Notice that I can take that guy by itself and say revolve it about the z-axis by 90 degrees. 90. It didn't do the bottom one. The bottom one, see that? The bottom one is still there. Another one. This circle. About the z-axis. 90 degrees. You see this? You see this? Again, this horizontal one, z-axis. Try it again. Z-axis, that's what I meant, not y-axis. It says I can't do it with y-axis. Oh, wait a minute. What happened here? Hang in there. Okay, okay, take it easy. Oh, there. Z-axis. I don't know what those sounds were for. That's what I was trying to do. Now, are there any questions so far? And you might say, well, why did you want to do this whole thing? Because I want a solid object here. You see this? I want
I
a solid
have a
object.
question.
Yes, yes.
So why do you do it one by one? Why do you just do it with the whole
Because that,
thing?
okay, if I do the whole thing, there is no problem. I can do that. But I want to create a solid object just for this circular arc. Okay, you'll see that. You'll see that in a second. Just bear with me for a second. You'll see it. Now,
Okay.
I want to go make a solid object. So obviously you have to go to part design. And there's something called thickening, not sickening, thickening a surface. Click on it. You select that surface in both directions, 1 inch out, 1 inch in. You see this? If I had done the whole thing would have been, a solid object. And I don't want that. All I want is solid object here. That's it. I don't want this. Because I want to mesh this thing with tetrahedral element, with pyramid, with solid element, and these with shell elements. You understand why I did this thing like that? And I'm not saying this is the only way. I just wanted to show you some features that you may never have touched, and it's very useful. That business of basically getting a profile out of a sketch, something very useful. Think about it. Think about it. Okay, good. So look at what I have here. First of all, let's make everything out of steel, by the way. So apply material, everything out of the steel. Move this thing out of the way. Okay. And save it. Okay. By the way, notice that here, you see this? This is a surface. This is that circular surface. So I can hide it. If you don't want to do anything with it, just hide it right there. These are profiles. If you don't want them, you don't need it, of course. You hide it so that it goes away. You don't see it anymore. Right there. See? Excellent. This is my cylinder in the 3 problems that you have done in class. This is that plate, for example. I don't have beam element. This is the plate. This is the plate. Think about it. They're coming together. Okay. Now, as far as part is concerned, we're done. So we're going to go to a generative structure analysis. CATIA sees a solid object. It jumps on it and measures it right there. You see this? It doesn't mesh the surfaces for you, but it jumps and meshes this. If you look at your mesh, you can see that only the solid is done. The other ones you still have to do the usual way. Yeah, right there. You see this? And deactivate it. You can put the cursor here, deactivate. Okay, good. We have to do the shells. Octree triangle mesh. I hate that word. I don't know, 1. Let's make it 1 and see what happens. By the way, this is parabolic. Probably the other one was parabolic too. If not, they don't have to be, but fine. I don't know what the other one was. The one that CATIA did for us. Oh, parabolic. Okay, fine. These are simple problems. Thickness. Thickness. Help me. What is the thickness? Right there, 2. This is why when I created that thickening effect, I went 1 inch out, 1 inch in. That's a total of 2 inches. But these other ones are shells, so same thickness. Oh, did I do that? Yeah, 2 inches. Here's what I typed, 2 inches. I did that earlier today. Okay, yeah. Okay, let's do the other one. Is there a question? I guess not. Okay, let's mesh this guy.
Just a question with thicken. Does CATIA thicken it both ways by 2 inches, or does it thicken it one way by 2 inches?
Actually, you mean for shell or for this 3-dimensional object? Which one? Which one?
Well, for the shell, because a 3-dimensional object is the object.
Yeah, for the shell, when you say the thickness is 2 inches, it goes 1 inch in one direction, 1 inch in the other direction. So that this is the middle surface. Okay? So this is the total thickness. Half of it is one side of the surface, half of it is in the other side of the surface. In general, that's how thickness works. This is why when I try to thicken, not thicken, thicken that surface here, I say go 1 inch in one way, 1 inch in the other way, so that you get a total 2, so that it matches that. Okay? So let's do the bottom, right there. Okay, fine. Thickness, 2 inches, 1 inch up, 1 inch down. That's the way it does. Shell elements work like that. Okay, so what do we have here? Now, these are planes of symmetry. Remember, these are planes of symmetry. So first of all, surface slider here. This is a solid. Turn it around. Here. Okay, very good. User-defined restraint. Uncheck that. So this edge and that edge, they lie in your XZ plane. XZ plane, do not move in Y. Rotations opposite. I did 90 because I didn't want to create a local coordinate system. Remember that guy? 45 degree. We have a problem. There we are. Again, the other two edges, this guy and that guy, they lie in the YZ plane. They don't move in X, and rotations are opposite. Excellent. Let's go and save our analysis before we regret it. Save management, analysis, save as. This is the right folder, lecture section 2, PV, pressure vessel, analysis, very good. Please learn how to save the names properly to submit on the test. Not like this. Okay, good. Pressure, 300 PSI. Where is this guy? Pressure, where's the load? Oh, right here, right here. .300 PSI. Listen, some of these hydrogen tanks that they use in cars, the pressure goes up to, I don't know, 500-600 PSI. Okay? There. Is that the right way? Yeah, that's good. There. Is that the right way? Yep, that's good. And there. Yeah, that's good. I like it. Okay. Save it. And if you run it, it's going to bomb out because these guys have no idea the other guy is present, so we create connections. So connection between this face of the solid, that face of the shell. This is going to be fastened. Same thing down here, up there actually. This guy. And for the second component, that guy. Okay. And where is this hanging there? This is fastened, right? I said fastened. Okay. Fastened right here. This guy is a fasten. There's your good old fastener sign. Is that the second one? Yep. There's the good old fastener sign on the other side. Save everything. Save everything. Save everything. Would you like to get full mark on this? This is a hybrid problem, right? It has 40 marks. Would you like to get full mark? Then do something that you forgot or I forgot. What would that be? I forgot something that is going to take off about 6-7 marks from me. What do you say? What other symmetry we have? Isn't this a plane of symmetry? Isn't this a plane of symmetry? Top. Yes, that's good. You're absolutely right, Fabio, sorry. Okay, so you want to get full mark? Okay, no problem. And check all of these. Take the top. It's in the XY plane, does not move in Z, and rotations are opposite. We say good, we save it, and then run it. Always pray, always pray, particularly before the test. It just says that the elements are not very good looking, basically. It is bad. Remember, I told you these problems, these elements, you got to be very careful. They may run, but even the results are not reliable, may not be reliable. We know that none of our results are reliable anyway, because we're not doing any mesh convergence study. But this is complaining already about something. Let's run it and see what happens. We did. Let's look at deformation. Okay, first of all, I don't want to see all this junk. These are all the extra elements that are created because of the fasten connections and things like that. Let's just see the octree triangle and this and the solid one, so that we don't get that junk. Anything that we don't like, we're going to hide. Okay, so and you can see easily, you will see easily why we got that message. So let's hide the properties. Let's hide the, I don't know, restraints. Let's hide the load. Not that, not paste. Hide it, I meant hide. Okay, let's hide the connections. Hide these elements. Let me hide the whole thing, see if it works. Good. If you looked at this result, it already tells you what the problem could be. Look at the way this shading, look at the shading. It tells you this is not a fine enough mesh. You can see that. You see? Because these are supposed to represent that surface. Yeah, they do, but if they're that good, I will not get a lighting like this. Okay? So that message is saying that these are not very good elements, okay, or the mesh is not very good. Okay, let's look at the stresses. Change the rendering. There we are. Okay. Already tells you that although I don't have a 90-degree angle at that juncture, but I have a rapid stress variation there, which is representative of this red color. The colors change very rapidly, so there is definitely the stress concentration here. So the results for stress are okay there. Okay, and if you're lucky, we are okay here, but not in that area if you use all shell elements. Okay, now if you go and create a mesh like this, it's going to be a lot better. There's no doubt about it. I mean, you already know that. Don't trust any of these because we haven't done a mesh conversion study. You know that. You know that. Okay. Are there any questions? Are there any questions here? Because I want to show you something.
Yeah, I have a question, Professor.
Go ahead. Go ahead.
When you do the the revolve, I think.
Yes.
Of the
For
line?
surfaces.
Yeah.
Yes.
Yeah. How do you select which side the pressure will end up going on?
Okay. If you look at it and if it's wrong, then just put a minus sign. Just put a minus sign.
It just when I did it, it does it on the opposite sides of the shells, but on the right side of the solid. So it just
Okay, here's
makes
what
you
you do then.
two
If
different
okay,
ones.
that's easy. Yeah, that's easy. If that happens, do three different pressures. Whatever is right, leave it. Whatever is wrong, change it. In other words, I did it. I was lucky that all three of them worked out the correct way. But if you are saying on these two are okay, on this one is wrong, or the other way around, just do it three different types, because you don't have a control over that unless you do something. You don't have a control over that. The only control that you have is the put a minus sign. So do a pressure here, do a pressure there, do a pressure there. If any of them is wrong, put a minus sign.
Okay, thank you. I was just wondering if there was like an arrow that you could click, like on join, to switch
No.
the sides.
Oh, it has something to do with join. Yes, we don't have a join. Yes. In fact, when you talk about the surface has a positive side and a negative side. That arrow that you see when you join things, that gives you the direction of the positive side. And pressure is always opposite to that. Pressure, remember pressure, whenever you put is compressive, right? On any object, when you say 50 psi, it means that you're pushing into it, okay? So it has something to do with that arrow, which we don't have here because we did not join, by the way. So if you want to have a control over those things, you better join these surfaces individually, and then you can flip it, and that takes the correct pressure side, okay? Because we didn't join it, we didn't have to, we didn't join it. That's why the only control that we have is the sign of that P. That's all. Okay? Now, I want to show you something here. This is finished, but I do want to show you something. Let me cancel this. Let me cancel this. I want still my product and my part, not the product. Okay. So that analysis is gone. I want to show you something. This is the one that you saw a few minutes ago. Okay. Let me go to Advanced Meshing Tools. I want to show you something. Advanced Meshing Tool. When you go to Advanced Meshing Tool, CATIA doesn't do anything for you. Only if you go to Generative Structure Analysis, which says, oh, if I see a solid, I'm going to mesh it. But if you go to the Advanced Meshing Tool, CATIA won't even do that for you. So let me do the following. Let me mesh this. Let me extract this face, which I should have done a minute ago before I came here. So let me go back to my part. Generative Structure Analysis. Extract a face because I want to mesh it. Extract a face. This face. I want to extract this face. Surface. Okay, now I go to my analysis. There we are. You see, there's a surface here. And I can measure it with this fancy surface measure. Okay, so there. Okay. Okay, measure. It looks like that. Okay, it's a horrible mesh. I want it small. We can make it smaller, no problem. So double click on it. Double click on it. Okay, I guess you exit and then double click on it. No problem. Okay, so one is not good. So let me put I don't know, 0.4, 0.2, okay? 0.2. 0.2. Okay, don't worry about it. Say okay. Mesh it. I call it zap it. There we are. Is that good? Is that good? Okay. So I created these elements. These are shell elements, actually, because I did it on a surface. Now I can take this thing and basically extrude them through this part and create solid elements for you. Okay, so let me do that. First of all, we have to exit this. We have to exit that. And then if you look at these, you recognize beam, you recognize this guy, you recognize the one that I just used. Okay, we haven't used it much, but none at all, actually. Sweep 3D. Okay, you got to read it carefully. See what it says. Select the volume to mesh. See at the bottom left corner? At the bottom left corner, select the volume to mesh. Now, the volume to mesh for me is this guy. Let me try to select it from the tree. That's thickening, not sickening, thickening. Where is that? This guy. Okay. All right. And then it says bottom. So this is the bottom. And then it says the top. Top means the other side. The other side. This side. And then it says how many? Let's put, I don't know, 30. 30. Try and pray. Okay. So let's go to advanced. The rest, obviously, you have to mesh this and etc. But I'm going to go to generative structure analysis because I want to show you the mesh. It's very much easier to see it in the mesh, in the generative structure analysis right there. And you can see there is some order here. That's why these elements are better than that guy. Okay, so you're not responsible for advanced meshing tool. You're not responsible for this kind of a mesh, generating this kind of mesh. But the fact that you're not responsible means that you should know for future, for your own good. Okay? All right, folks, are there any questions? No questions. Excellent. So we're going to stop the class here. We're 10 minutes early. Perfect. I will be around for 10 minutes if you want to ask any questions. Some people don't want to ask while others are listening. So I'll be glad to be here. Do you have a question? No? All right, you're welcome.
I have another question real quick. When I tried to use the surface mesher, it selects the whole body. I don't know if you mentioned that, but
let me see. Are you talking about the one that the stuff that I just did?
yeah. When I try to click on the face, it won't.
Okay, so let's try this out. I'm gonna stop the recording so people can go if they want to, and then I'm gonna answer your question. Okay, just let me stop the recording here. I think it's this, and then we're gonna stop the recording.